right, today we're going to take a look at other set operations and their properties. We started talking about some set operations last time. One in particular, the one in particular we talked about was complements. Do you guys remember that? So the idea of complement is you take a set and you take everything that's not in that set. And that's the complement of the set. So we're going to take a look at 4 different operations on sets today, and these are the first 3. The first one is the set intersection. And the image you want to have in your mind is sort of like the intersection of 2 streets, right? So when we talk about the intersection of the streets, we're actually talking about the place they cross in the middle. That is the intersection. We're not talking about half a mile back up one of the roads. Okay, so an intersection is actually the set of all elements common to both sets. And in terms of the let's say the set notation, it looks like this. Oops, let's start that again. So we have 2 sets, and we do their intersection. Intersection is an upside down U, right? Or sometimes students say it kind of looks like an N, the N for intersection. And what this is it's all of the elements X such that X is in A and X is in B. So it's in both sets. Both sets. The set union is all of the elements in one set or the other, and I put the phrase "or both" because I want you to understand it could be in both, and that would be all right. And that would be part of the union. So this is A union B. So let me show you the set notation. I'll describe one more item in this idea. This is all the items X such that X is in A or X is in B. So one of the imagery you have in your mind is a wedding. We talk about the union of a husband and wife, right? So the idea is that I get all your money and you get all my debt. No. I get all your money and you get all mine, and I get all your debt and you get all mine. We just join it all together, one lump sum of mess, right? That's union. Union means you get it all, everything the good, the bad, the ugly, okay? That's union. Relative complement is the language your book uses. I put in parentheses difference here because some textbooks will use the phrase difference to describe what you're about to see. And in particular, if you've taken contemporary math, that's the language used. This is the set of elements in one set that are not in another set. So it looks like a subtraction. Okay, so that's why some of the books call it a difference. And this is the set of all items X, such that we take the items in A, X is in A, because A comes first, and we remove all the items that are in B. So we say X is not in B. And technically, I guess you could put the word and or an and in between here. Both those things are true at the same time. We want to keep it in sort of pattern like before. So it's in A and it is not in B. It's okay. Try to tilt it as much as it normally is. Megan, can you still see? All right, so we're going to do an example, I've used this kind of an example before, but I've never written it out. So we'll see if it works when I write it out. Okay. So we have Mary, single mom with 1 child, Mark. Joe, single dad of 2 children, Jack and Jill. Mary and Mark get married, and they have 2 children, Anne and Andy. Okay. And we're going to find the following, and I don't have these filled in because my computer program won't do it very well. We're going to find M intersect J. All right, so M is Mary's kids, J is Joe's kids. Okay, Mary's kids, Joe's kids. All right, so we've got M intersect J. So what is the intersection in this description? What's going on here? Can you describe in words who this would be? Who's in this intersection? Okay, who are they? Which kids? Anne and Andy. Because they're supposed to be Mary's kids and Joe's kids. Okay, so this is Ann and Andy. Okay, so we're not talking about stepkid, we're talking about a biological child. Mary and Mark get married. Okay, so. No. Yeah, I told you I messed it up. Okay, so let's put Mary and Joe. Can we fix it? There, I think that fixes it.
Yes.
Okay. So we have Mom, Mary. Oh, see, I told you it was late last night when I was doing this, right? We've got Dad, Joe. And we got a bunch of kids. How many kids do we have, do you know? There's 5 kids talked about here. We get them all right. Yeah, and Ann and Andy are the 2 kids that they share, right? That they have as a couple. All right, let's try this now. What would M union J be? All of them. So this would be the family picture, right? Everybody gets to be in the family picture, even if they're estranged from the family, right? We're not happy about some of that sometimes, but yeah, we get them all in the picture. So we get Mark. We get, who's next listed? Jack and Jill. And then we have Ann and Andy. That's the union. And then let's do the difference, or the relative complement. M minus J. Okay, well, we haven't actually written these out, but who is in the set M? Mark, Ann, and Andy, right? Those are my people that are Mary's kids. Okay? Like, with the problem set up. Okay, so I understand. Got married, now they're all my kids, whatever. These are the 3 problems right here, okay? Conceptually, okay? 3, Mark, Ann, and Andy. We need to take Mark, Ann, and Andy. We need to remove any of those 3 that are also Joe's kids. Ann and Andy get removed. Mark is who's left. Are you with me? Everybody okay with that? Is that right? Oh. Alright. We have one more set operation that we'll hold for just a moment, and we're going to talk about the properties of these particular ones that we just encountered. So the first property we have is commutativity. I know you guys have heard the words commutative and associative and distributive before. We learned about them in terms of algebra. Does anybody remember what any of them mean?
So one might flip the turn.
Yeah, so one of them, I think the one you're describing, you can tell me if it is flipping the order of something, right? Like we talk about sometimes that, and we do this with kids, right, that if you know what 5 plus 3 is, then you also know what 3 plus 5 is, right? That's called commutative, so that's the order issue. So you think about commuting, that is changing the order, okay? So the commutativity of set intersection union says the following. I can do A union B or A intersection B, but I could do B union A and B intersection A. The order I do the union or the intersection doesn't matter. It doesn't change anything. Are you following? Okay. And so this is actually true for all sets A and B. Okay, so it isn't really specific about it. It doesn't matter what those sets are, it has this property. Let's go back to medium then. Associative. It is when the grouping changes. Very good. So we have this property, or you probably remember this property of addition, that when you add 1 and 3 and then you add 4, it's the same thing as adding the 3 and 4 and then adding the 1. Right? It doesn't matter where you sort of put in these groupings or these parentheses. And the way that I always remember it is that associativity has to do with associating things together. Right? We associate or we group together when we're talking about associating things together. So I'll do the same order I did a minute ago. So if I have A union B, union C, that's the same thing as A union B union C. And it works for intersections just as well. And again, this is for all sets. A and B. So the order of intersection, the order of unions, the grouping of unions, grouping of intersections, none of that changes the outcome. Just like with addition, all of this works with addition and whole numbers or real numbers, whatever too. Do you remember distribution? What did you distribute?
Sign.
You distribute signs sometimes. What else do you distribute? Numbers. Okay, what operations are we talking about here? Multiplication over what? I distribute the multiplication over what? Over the parentheses that do what inside? Addition usually, right? Or subtraction would work with me too. But typically, the general case that you guys have seen before is distributing multiplication over addition, right? You got parentheses going on, you got some multiplication outside, and then inside parentheses you got either addition or subtraction. Okay, so we're going to do the same kind of thing on this one, but this is the distribution of intersection over union. So here we have A intersect, and we have B union C. Okay? This is an intersection on the outside, union on the inside. Like we have multiplication on the outside, addition on the inside. Okay? And what we're going to do is we're going to distribute this. This A is going to distribute to the B, so this is going to be A intersect B. Kind of like we do with multiplication. And we're going to do the A with the C. A intersects C, and what do you suppose goes between them? The union. That's what happens when you did it with multiplication and addition as well, right? You distribute the multiplication, multiplication applies here, multiplication applies here, and we've got a plus sign in the middle. The original is plus, or minus, the original is minus. And again, this works for all sets A, B, and C. Now this should have said A and B and C. All right, so this is for all sets A, B, C. There is one other slide before we get to some examples, okay? So this slide, is everybody okay? Did they get that written down? All right. This slide has both a formula on it and it has one more set operation on it. The formula is coming first because it actually relates the other items we've talked about. This is called a cardinal number formula, and I'm not sure I found a specific location. I probably just overlooked it when I was trying to find it in your book where it explicitly states or at least gives it a name. It doesn't give it a name. But the cardinal number formula looks like this. The number of items in A union B is the number of items in A plus the number of items in B minus the number of items in the intersection. And I can draw you a picture of how that works pretty well. Okay? So I want you to imagine doing a Venn diagram. And we've done a little with Venn diagrams so far. We'll do more as we move on today. But imagine that you have a Venn diagram. So a Venn diagram, we'll get to here in a minute. But it looks like a rectangle with some circles inside. And my circle's inside. Oh, that doesn't look like a circle at all. Let's try that again. My circles inside overlap. There we go. Have I shown you guys how to clone things? Okay, once you have an object, if you want the same object again, you just select it. So if you noticed, I clicked on the arrow down here to select it instead of actually drawing on my board. It lets me move things around. So I've selected my object. This arrow over here on the right-hand side, I'm going to click it. I'm going to click clone right there. So clone is exactly what we mean by clone. It takes the same image as like copy paste. So we're going to clone it, and it draws me another image exactly like that one. And then I can move it there. Very nice. So now I have two images, which is what I wanted. I need to call them A and B. All right, so the picture of the union, again, should mean everything and both things all together. It's the family picture, okay? We get everything all included. So if I want to talk about that item and I want to talk about shading for that, I'm going to take this item and I'm going to shade and fill it in. So I'm going to fill it in, I'm going to use yellow. So this is my set that's going to be yellow. And then my set B, I want to do the same thing, and I want it to be something else. I'm going to make it red. That wasn't the best choice. No, we'll do it that way. We'll see if we can get it to work. Well, all right. I'm not going to get it to work the way I thought I would hope for, but that's okay. All right. Let's do this. I'll draw it in. That'll work. All right. So everything got colored in yellow, right, from the first circle. And everything got colored in red in the second circle. And I did something in the middle that I inadvertently did. I colored a little piece in the middle that looked like this twice, didn't I? I colored it yellow and I colored it red. And I was really hoping it would turn to orange. That didn't happen. So I've got this little piece in the middle that's been colored twice. So this cardinal number formula talks about taking sort of this image. This would be looking at the number of items in these two component pieces. The problem is if I count how much was out in the yellow circle, and I count how much was out in the red circle, I double counted the part that was in the middle twice, right? Well, I double counted it once, I counted it twice. So I counted it twice, which means I'm going to subtract off one of those counts. Think back to Joe and Mary, right? If I wanted to do this with Joe and Mary, I wouldn't count all of Joe's kids because he had 4, and all of Mary's kids because she had 3, and say that they had 7 kids. Would I? No, because if I do that, I counted Ann and Andy twice. Everybody following? So if I do this sort of counting, I end up double counting the part where they overlap. That overlapping part is actually called the intersection. So that's what you're seeing happen. Okay, hang on. There we go. That's what you're seeing happen on this particular formula. Is you're seeing a formula that relates this idea of taking out that double count. Now we have one other issue to talk about, and that's Cartesian products. Cartesian products actually come from the most related idea that you've seen before is ordered pairs in algebra, like points in a coordinate plane, XY pairs. And you see this ordered pair idea here as well. So this is the set of all ordered pairs such that the first component comes from the first set and the second component comes from the second set. And I'm going to do an example so you can see how this works. So let's create a set A. And we're going to let set A be 1, 2, 3. And we're going to let set B be A and X. So we've got 2 sets. They don't necessarily have to be the same size or anything like that. What we're going to do is we're going to create another set. So this set, Cartesian product, is the set A cross B. So it kind of looks like multiplication, right? Okay. So my set is going to be a bunch of ordered pairs. I take the first component of the first set, which was the number 1, and I make it the first component in my ordered pair. And then I take the second value in the the first value in the second set, and I make it the second value of my ordered pair. Okay. So I take the number 1, I take the letter A, and I put them in as an ordered pair. Now I'm going to take the number 1 and the other item that's in set B, which happens to be the letter X, and make an ordered pair. That is all of the ordered pairs that can be made that have the number 1 in them. So I don't need the number 1 anymore. I'm moving on. I've got the number 2. I'll do the number 2 and the first item in the second set, which would be A. And then I'll do the number 2 and then the number or the letter X. Okay, that's all of the items that have the number 2 in them. And then we're going to move on to 3. 3 and what? A. And then 3 and X. And this is all of the combinations. Right? How many of them are there? There's 6. So I want you to notice a relationship here. I'm going to make a relationship between the number of items. The number of items in A. How many items were in A? There were 3. How many items were in B? There were 2. And how many items were in A cross B? 6. So you guys had an opportunity to do something similar to this in your homework. What is the conjecture you can make between the relationship of these sets? What is it, Kayla? Is it
like 3 times 2?
Okay, so 3 times 2 gives me the 6, right? So the number of items in the Cartesian product is the same thing as what? What do I do with the 6 and 3 and 2? What do I get? I want to multiply the 3 and the 2, right? 3 was the number of items in A, yeah?
Yes.
And I'm going to multiply that here by the number of items in B. Now, that's not telling you the items in the set. So be careful anytime you're looking at directions, right? Are the directions asking you for the set, that is, the A cross B, or are they asking you for the number of items in A cross B? That's different, right? A cross B we did and we wrote it all out. This is A cross B. This is the number of items in A cross B. So if I'm finding the number of items in A cross B, I don't actually have to draw these ordered pairs out. But if I'm asked to find A cross B, I do. Are you with me? It's a different question. Am I asked what the set is, or am I asked how many items are in it? All right, so we need to do some examples of these. Are you guys ready? We're going to do some examples of some Venn diagram shading. All right, so as I said before, the program limits me in what I can put in, so I'm going to put it here. This is A complement, union B complement. And we're going to do this with Venn diagrams, okay? So in my Venn diagrams, I need 2 circles inside of a rectangle. Everybody with me so far? I'm going to call these set A and set B. And they're inside of a universal set U. I'm going to show you how we're going to do shading. Okay? And I really want to see you do it this way. There's lots of ways to do the shading. The reason I'm going to show you this for this example is because because you can do this without what I'm about to show you pretty easily because there's just 2 sets. When we get to 3 sets, it becomes very cumbersome to do much else besides what I'm about to show you, okay? So just bear with me on the easy case. I'm going to show you what happens with the method, then I'm going to show you on the easy case, and then you'll see why we did it when we use the hard case, okay? What we're going to do is we're going to give each of these regions a number. This region is called number 1. This overlapping in the middle is called number 2. Region 3 on the outside of B, and then region 4 is on the outside of U. There are 4 distinctly different areas of this shape, this curve, this picture diagram, okay? So far so good? Okay. The numbers 1, 2, 3, 4 are labels. They're not really numbers. They're not numbers of items, they're not elements, they're just labels of the place we're talking about. So I can say number 1 and you guys look at it and you know where I'm talking about the picture. Okay? Alright. What we're going to do though is we're going to create these items based on the numbers we just created. A complement, based on the numbers 1, 2, 3, 4. Which of these numbers are in A complement? 3 and 4. B complement. which of these numbers are in B complement? 1 and 4. And we're going to do this kind of like when you did addition as a small child, right? What I want to do now is to take both of those and I want to combine them, and my combination is going to be the union. So A complement, union, B complement. But you have to pause and think to yourself, what does union mean? It means joining everything together, right? It's the family picture, everybody gets included. So, what is A complement, union, B complement? 1, 3, and 4, all of them. And in your picture, that is the solution, needs to be a shading based on that. So I come over to my picture and I shade region 1, region 3, and region 4. That's the answer. That answer will get you just about 0 credit if you don't show me the work that I'm showing here. Okay? I expect to see this work. Now, part B, or section B, part B, whatever on here, becomes much more evident of why. So let's take a look. We're going to do A intersect B, in parentheses, union C. So all of a sudden I take something that had 2 circles, and now how many will I have? 3. I need 3 circles. They all need to overlap, and kind of looks like what you would have if you had, the Olympic rings. Okay. I think I got enough space there. All right. So I have sets A, B, and C, and here's set U on the outside. Marks are good. I do not have 4 regions anymore. I have 8. And I tend to number, and your book does this too, they use letters, but I number mine with numbers. 1, 2, 3, 4, 5, 6, 7, and 8. Okay? You'll all just do me the favor of humoring me by numbering the same so that I don't go crazy trying to figure out where your numbers go to. Alright, so we're going to do the same thing that we did just a minute ago. We're going to list the numbers in each set. Alright? A is my first set. Which numbers represent region A? 1, 2, 4, and 5. How about set B? 2, 3, 5, and 6. Why did I do A and B first? Because they're inside the parentheses, okay? That's important. We're working just like you do in algebra, inside out. Okay, so inside of the parentheses, move out. All right? Now I'm going to do just like I did before. I'm going to join these with the operation, and this operation is intersection. What do I look for if I'm looking for intersection? What's in common? And what numbers do you see in common? 2 and 5. Okay, so that's my intersection. Oh, how did I get an extra equal sign? I don't know. Let's try that again. Okay, so this is 2, 5. So that's everything inside the parentheses, and then we move outward. The next set on the outside of the parentheses is set C. What is set C? 4, 5, 6, and 7. And then I'm going to join those together with which symbol? Union on this one, yes. So this is A intersect B, and I'm going to do a union with C. And what does union mean? Everything. We get everything. So I have 2, 4, 5, 6, and 7. And on my picture, I shade exactly those 5 areas. I shade in 2, 4, 5, 6, and 7.
Bottom there, is it intersect C or?
Oh, it was supposed to be union. I just wrote the wrong one. Let's fix that. Thank you. Yeah. Okay, we have one more picture for shading, and then we'll stop for today, okay? So let's flip to the next slide. This is our last shading picture. And we're going to do A intersect B complement intersect C complement. All right, so I need my rectangle. Where do we want to start? A. What numbers are in A? What's next? B complement. Inside parentheses, right? Which numbers are in B complement? 1, 4, 7, and 8. It's everything outside circle B, right? 1, 4, 7, and 8. And how am I going to join these? Intersection, which means what will I be including? What they have in common. What do they have in common? 1 and 4. All right, then what? C complement. Yeah, we'll do the intersect part next, but let's just do C complement first. What is C complement going to be? 1, 2, 3, and 8. And then what? I'm going to do an intersection of those. So A intersect B complement. All of that is then intersect C complement. What am I looking for? What they have in common. And this is only the number 1, isn't it? So my picture I get that little portion. Any questions on the shading one?
So once we get down to whatever we get down to, that's what we shade.
Right. That's right.